Hi, I'm Rajshri Chakrabarti, a PhD student in the group of Professor Peter Vekelov, and today I'm excited to share a part of my PhD work on solute-solvent interactions during organic crystallization processes. So in the first part of my talk, I will be talking about solute-solvent interactions and their effects on the thermodynamics of crystallization. And in the second part, I will be talking about solute-solvent interaction and solvent viscosity effects on the kinetics of organic crystallization. So solution crystallization is an essential step in many natural, physiological, and industrial crystallization processes. Some of the examples are shown here, like the naturally occurring crystals of ice, huge crystals of selenite, which grow in the caves of Mexico. They all grow from a solution, and crystals growing in physiological conditions like cholesterol, insulin, kidney stones, industrially engineered crystals which have a variety of use like zeolites, pharmaceutical drugs like ibuprofen, they all employ solution crystallization. And in recent years, organic liquids are the solvent of choice for crystallization, separation, and purification of small organic molecules like active pharmaceutical ingredients. Again, some of the examples are shown here like apomorphine, dopamine. Organic liquids are also used for the crystallization of specialty chemicals known as porphyrins. Porphyrins are organic molecules, and because of their delocalized pi electron, low symmetry crystals of porphyrins are used in electronic devices like semiconductors, solar cells, etc. So to have a good understanding of solute-solvent interaction during organic crystallization processes will help us design robust crystallization processes. And with this in mind, we study solute-solvent interaction, and we choose etioporphyrin 1 as the solute of our choice because it crystallizes in the same polymorph irrespective of the solvent, giving us an opportunity to study the solute-solvent interaction in the solution phase. And it is crystallized from 5 organic solvents, which are shown here to highlight the role of several solute-solvent interactions like permanent dipole interaction between the polar groups of the solvents like the sulfonyl group of DMSO and the polar pyrrole group of the solute. And it has four, etioporphyrin 1 has 4 pyrrole groups. And we also use alcohols, which has polar hydroxyl group, very similar dipole moments though. And the choice of these solvents can highlight the role of London dispersion interaction between the solute and the solvent, between the nonpolar parts of the solute solvent specifically. So DMSO has very short alkyl chain length, and the alcohols butanol, hexanol, octanol have increasing alkyl chain length, and etioporphyrin has methyl, ethyl, and methine groups as the nonpolar groups. And finally, we use caprylic acid with COOH group to see if there is any kind of salt bridge formation between this COOH group of caprylic acid and the pyrrole nitrogens of etioporphyrin 1. But before we go into determining the thermodynamic parameters, we crystallize etioporphyrin 1 from all these 5 solvents by slow cooling. And what we see that it has a plate-like morphology in the alcohols as well as in caprylic acid, and it is more isometric in DMSO, indicating different rates of growth in different solvents, which is quite intuitive. And when we look into the powder X-ray diffraction pattern, what we see that the powder diffraction patterns of the crystals obtained from different solvents are identical to each other, and it's identical to the commercial stock. And they all belong to the same polymorph, which was determined using the Cambridge crystallographic database. It belongs to the P1 triclinic space group. Now, in order to determine the thermodynamic parameters of crystallization like enthalpy, entropy, and free energy, we use the Van't Hoff's law, which relates the solubility variation in temperature with the enthalpy and entropy of crystallization. So this is a plot of solubility variation of etioporphyrin 1 with temperature when it is dissolved in these 5 solvents. And what we see is that the solubility varies exponentially with temperature. This is the same plot of solubility variation with temperature, but it is plotted in the Van 't Hoff's coordinates. And the slope of these curves give us the enthalpy of crystallization and the intercept, the entropy of crystallization. So the determined values of enthalpy of crystallization is shown here. What we know one thing, that the crystals that are forming in all these solvents are identical, indicating that the enthalpy of the crystal is uniform across the solvents. So the enthalpy of crystallization in different solvents depend on the solution enthalpy of etioporphyrin 1 in different solvents. And this is actually a comparative schematic plot of solution enthalpies of etioporphyrin 1 in different solvents. And understanding this solution enthalpy will give us an insight into the different solute-solvent interactions and which interactions dominate the solution thermodynamics. A lower solution enthalpy indicate a stronger solute-solvent interaction. Now, when we look into DMSO and hexanol, we see that these two solvents have very different dipole moments and the alkyl chain lengths are also different, but DMSO has similar interaction to that of hexanol because of the strong dipole-dipole interaction between the polar pyrrole groups of etioporphyrin shown here in blue and the sulfonyl group of DMSO. If we look into the alcohols, we see a trend that with increasing alkyl chain length from butanol, hexanol, octanol, the solution enthalpy decreases, indicating a stronger interaction. So that is because of the increasing alkyl chain length of the alcohols. With increasing alkyl chain length, the van der Waals interaction between the nonpolar parts of the solvent and the solute increases, and thus we see a lower solution enthalpy for octanol. When we look into caprylic acid, we know that it has a substantial amount of dipole-dipole interaction with the pyrrole groups of etioporphyrin and a long aliphatic chain, very comparable to that of octanol. And thus it has a strong van der Waals interaction as well. And, and hence it has the lowest solution enthalpy of all the solvents. When we look into the entropy of crystallization, we see that they are all negative, indicating that solute molecule loses degrees of freedom upon incorporation. But when we look into the trend of the entropy and enthalpy of crystallization across different solvents, we see that they are very similar. And this conformity of trends for enthalpy and entropy of crystallization suggests that the solvent structuring at the crystal interface is weak and it's only supported by solute-solvent interactions. Organic liquids, unlike aqueous solutions, have very weak solvent-solvent bonding, and as a result, a strong structuring of solvent doesn't occur at the crystal interface. And finally, to understand if there is salt bridge formation between caprylic acid and etioporphyrin 1, we dissolve etioporphyrin 1 in caprylic acid and acetic acid, and we record the UV-vis absorption spectrum. Now, what we see in the absorption spectrum is a merged Q-band of etioporphyrin 1 in acetic acid, which is a signature of salt bridge formation. So we see salt bridge formation in acetic acid, but while in caprylic acid, we see the 4 intact Q-bands of etioporphyrin 1, as it can be seen in other solvents also, which has only permanent dipoles and van der Waals interaction. So this indicates that caprylic acid doesn't have salt bridge formation. And another important factor to notice here is solvatochromic effect. So in all these 5 solvents, which have very similar interactions like van der Waals interaction, permanent dipole interaction between the solute and the solvent, we see a very similar solution color. While acetic acid, which has salt bridge formation, has a different color. So solvatochromism can be used as a sensitive tool to understand solute-solvent interactions. So after understanding the solute-solvent interactions, we move into the kinetics of crystallization. So crystals grow by spreading of layers as shown here, and the step velocities are the rate of attachment of solute molecules to the crystal, and it depends on the solution supersaturation. and Ce is the solubility, and beta is the rate constant or the first order rate constant for molecule incorporation into the steps. It depends on the solute diffusivity and the activation energy barrier for molecule incorporation into the growth sites. So the solute diffusivity is actually inversely proportional to the solvent viscosity. So the step kinetic coefficient is inversely proportional to the solvent viscosity, and it also depends on the activation energy barrier. So in order to quantify the kinetics, we measure the step velocities on the flat face of etioporphyrin 1, which is actually the O1O phase as identified by single crystal X-ray diffraction. We measure the step velocities in situ using atomic force microscopy. And what we see is that the crystals grow by spreading of layers and from screw dislocations irrespective of the solvent. So we use two groups of solvent, DMSO, and the alcohols, butanol, hexanol, octanol. With increasing alkyl chain length of the alcohols, the viscosity increases, and DMSO, which is the smallest molecule, has the lowest viscosity. But irrespective of the solvent, the crystals have very similar growth hillock morphology in all these solvents. And we measure step velocity by monitoring the step displacement with time. So this is a variation of step velocity with the solution supersaturation. And we see that the step velocities vary linearly in all the solvents, and the slope of these curve can give us the step kinetic coefficient. So the determined values of step kinetic coefficients are shown here, and these are the solvent viscosities. So when we compare, we see that with decreasing solvent viscosity, the step kinetic coefficient increases, but DMSO, which has the smallest solvent viscosity, has actually a lower step kinetic coefficient, which is quite counterintuitive. And when we look into this plot, the difference is quite evident that for alcohols, the step kinetic coefficient scales with the viscosity, while in DMSO, it's actually a factor of 2 lower than the alcohols. And in order to understand this discrepancy, we look into the activation energy barrier. In order to understand the activation energy barrier for molecule incorporation into the growth sites, we have to first know whether the crystals grow by direct incorporation of solute molecule into the growth sites from the solution, or whether they have surface diffusion. So in surface diffusion, the solute molecule absorbs into a terrace, and then it diffuses towards the kink. So in surface diffusion, because of competition between closely spaced steps for solute molecules, the step velocities will be lower. So we measure the step velocities of closely spaced steps and well-separated steps. And what we see that both double and single heighted steps have very similar velocities in octanol. And the same thing can be seen in all these solvents where the step velocity variation is independent of the step separation, indicating that it is indeed growth by direct incorporation. And then finally, we use all atom molecular dynamics simulation to calculate the mean free potential of molecule incorporation into the kink. And what we see that is in the alcohols, the activation energy barriers are very similar because of similar interactions at the kink or the growth sites. And the highest barrier can be seen in the case of DMSO. And what we see in general is across solvents, we see a multiple intermediate step for molecule incorporation into the kink. And in order to understand the highest activation energy barrier, we look into the kink, and DMSO being a small molecule, the number density of DMSO, that will be structured at the kink, will be higher than the alcohols. And DMSO will have a strong interaction with the pyrrole groups which are exposed at the kink, causing the activation energy barrier higher. And hence the solute molecules will have difficulty in incorporating for DMSO, and hence we have a lower step velocity for DMSO. So now we have looked into the effect of solute-solvent interactions on the thermodynamics, and we have understood how it affects the pathways of crystallization, whether it's direct incorporation or surface diffusion, and also the effect of solute-solvent interactions on the kinetics. So I would like to conclude saying thermodynamic parameters of crystallization can be evaluated from the solubility variation in temperature, and for our tested pairs of solute and solvent, the interactions are dominated by permanent dipoles and weak van der Waals forces, as a result of which the solvent structuring at the crystal interface is negligible. But we have also shown that because distinct solute-solvent pairs have distinct activation energy barriers for solute incorporation into the kink, and for solvents which are like the homologous series of solvents, that is alcohols, the step kinetic coefficient scales with the solvent viscosity. So these insights will help us design robust organic crystallization processes. And with this, I would like to post my acknowledgements for my advisor, Peter Vekelov. Lakshman G. Verma did all the molecular dynamics simulation work. Our collaborator, Dr. Jeremy Palmer at UH, and Dr. Monica Verzecha at Strathclyde. And special thanks to Drs. Jeff Reimer and Dr. Caroline Muller, and our funding source, NSF. With this, I would like to encourage each and every one of you to go and check out our paper on solute-solvent interactions and their effect on the thermodynamics of crystallization, which was published in Crystal Growth and Design. And I'm really thankful for everyone's attention. And I would like to answer any questions that you may have in the live chat session. Thank you.